Welcome to Advanced Quantum Chemistry and my third lecture on density functional theory. The topic of this lecture is Kohn-Sham density functional theory, which was developed in 1965. In the last lecture we concluded that these early orbital-free density functional theories like the Thomas Fermi or the Thomas Fermi-Dirac model were not good enough for being useful in chemistry. Whereas Kohn-Sham density functional theory is not orbital-free density functional theory, as we're going to see soon, and it's the basis for the success of density functional theory in chemistry. But this has a price, and the price is that orbitals were reintroduced again. So it's density functional theory, but with orbitals, which of course means that the part of the idea that one only needs a quantity which depends on three coordinates x, y, z, the density in order to calculate the energy, is lost again. Now, the kinetic energy contribution is the problem, or was the problem, in these early orbital free density functional theories. And let's look here at, for example, the energy of neon, where you can see the kinetic energy contribution is 128.5 atomic units. The exchange contribution is minus 12.1 atomic units, and the correlation contribution is only minus 0.4 atomic units, meaning the kinetic energy contribution is the largest contribution there, and if you don't get this one right, then your energy is obviously not going to be correct. The idea of Kohn and Sham is then, or was then, to express the functional, the kinetic energy functional, as one contribution, which is the kinetic energy of a reference system for which one can calculate the kinetic energy correctly, and then a correction. Now this reference system, that's a hypothetical reference system of non-interacting electrons, but with the condition that the density of this non-interacting reference system is equal to the exact density. Now, because it is a reference system of non-interacting electrons, the wave function of such a system of non-interacting electrons, of course, can be written as a single Slater determinant, which we call the Kohn-Sham Slater determinant, which is again just a normal Slater determinant, meaning an antisymmetrized products of orbitals, which are we call the Kohn-Sham orbitals. And in order to calculate density of such a single determinant wave function, we had that in the last lecture. If one calculates the density of that, this is just the sum over all the occupied spin or spatial orbitals, and then the norm squared of the orbitals evaluated at the point where one wants to calculate the density. So that's a very simple expression for the density, but this density, I mean, the orbitals have to be chosen in such a way that the density calculated in this way is the same as the exact density of the system. Now, for a single Slater determinant, of course, we know how to calculate the kinetic energy contribution. So this kinetic energy function of this reference system is exactly known how to calculate that. The unknown, of course, is then this correction. So the energy in this Kohn-Sham density functional theory is then a function of the density, where we have as the first contribution this kinetic energy contribution calculated from this reference system, meaning exactly the same expression as we would have in Hartree-Fock theory. Then we have an electron nuclear attraction contribution, we have an electron repulsion contribution, which we calculate also from the orbitals again. And we have then sort of a correction term, all the things which we haven't included in here. So this is the expression as we had it in Hartree-Fock theory for the kinetic energy of a single determinant wave function, here with the orbitals, Kohn-Sham orbitals. Then the electron repulsion contribution is also calculated from this reference system, which means this is just the Coulomb term of, as we had it in Hartree-Fock theory. And this rest, this correction, is now what is missing in the kinetic energy. So it's the difference between the exact kinetic energy functional and the one of our single determinant reference system, and plus the difference of the exact electron repulsion minus our Hartree-Fock calculated electron repulsion. And this is called the exchange correlation functional, because we have sort of correlation here, we have correlation there. And of course, what is also mainly missing in here is the exchange contribution, because this is just the Coulomb term of Hartree-Fock theory. Now, what they had to do then is derive equations for these orbitals, which guarantee that the density calculated from these orbitals is equal to the exact density of the system. So the density of this hypothetical non-interacting system is equal to the exact density. J here in doing that, and I'm not going to go through that, doing that led to this equation. An equation for the orbitals, an eigenvalue equation for the orbitals, where we have some operator acting on the orbitals, giving orbital energies back times the orbital. So it's an eigenvalue equation. And this, of course, looks absolutely the same like the Hartree-Fock equations. So it's exactly the same equation like the Hartree-Fock equation. The only difference is that the Fock operator here, the Kohn-Sham Fock operator, is slightly different than the Hartree-Fock Fock operator. I've written it up here. We have the kinetic energy contribution. That's obvious because that's how we calculate the energy. We have the electron nuclear attraction term, which is precisely the same as Hartree-Fock. So we have the core Hamiltonian as in Hartree-Fock theory. We have the Coulomb term, and on the next slide I'm going to show you that this is exactly also the same as Hartree-Fock theory. And then we have something new, which is different, which is this which is the exchange correlation potential, and that is calculated as the functional derivative of the exchange correlation contribution to the energy with respect to the density. Now let's compare this Kohn-Sham Fock operator with the Fock operator from Hartree-Fock theory. The expression for the Kohn-Sham Fock operator, which we have here, we will see that it's exactly the same. So this Coulomb contribution, Coulomb electron averaged interaction, is the same in Kohn-Sham theory and in Hartree-Fock, which we have here. As I said before, the core Hamiltonian is exactly the same. And then in Hartree-Fock theory, here we have a Coulomb term with the Coulomb operator, and we have the exchange term with the exchange operator. And it's written again in spatial orbitals, doubly occupied spatial orbitals. Therefore, we have a 2 here. Now let's look at this Coulomb term a bit more in detail. Now the Coulomb operator, remember, that is an integral over electron 2. So we averaged over the positions of electron 2. So we have electron 2 described by some spatial orbital phi j, and because it's the interaction with all the other electrons averaged over their position, so I have a sum over all doubly occupied spatial orbitals phi j here. But this is an orbital complex conjugate times the orbital. This is just the norm squared of the orbital, so that's actually just the density of electron 2 coming from this orbital. And since we sum over all occupied orbitals here with a 2, this summation is nothing else as the total density of the second electron. So we can write this also with this density, and if we now with the corresponding expression for theory. The difference is therefore just in the exchange term. So where in Hartree-Fock theory we have this exchange term, in density functional theory we have the exchange correlation potential. And the purpose of this exchange correlation potential is not only to include the missing exchange term, but also to include all the missing correlation which we do not have in Hartree-Fock theory. Because remember that density functional theory should in principle be able to give the exact energy, meaning including all the correlation effects, all the instantaneous electron-electron interaction, which we definitely do not have in Hartree-Fock theory. The big problem of density function theory is therefore then, what is the precise form of this exchange correlation functional, and I will discuss that in my next lecture.